One interesting thing about geometric algebra is that in most cases, it doesn't really enable us to do anything new. Instead, it just helps us do things in a better way than before. Because of this, there are many things that people use instead of geometric algebra, and an exposition of geometric algebra wouldn't be complete without talking about them. Thus, after each chapter in From Zero to Geo, I'm going to be making an appendix of sorts where I go over some of the alternatives that relate to what we developed in the chapter. Before going into that, though, I want to mention that these appendices should be helpful whether or not you know about the alternatives. If you do know about them, these videos can help you connect geometric algebra with what you already know. Furthermore, these videos can help you see where geometric algebra improves things. If you don't know about the alternatives, just tuck some of these ideas away for the future for when you do inevitably come across them. At that point, being able to connect these other concepts with geometric algebra may give you a boost in understanding them. Anyway, let's get to talking about what people use instead of multivectors. First, let's talk about pseudovectors and pseudoscalars. Some of you may have been confused about me calling n vectors in n dimensions pseudoscalars. In some areas of math, and especially in physics, pseudovectors and pseudoscalars are already things that seemingly have nothing to do with geometric algebra. To describe the connection and why we use these already existing terms in geometric algebra, I will briefly cover what traditional pseudovectors and pseudoscalars are. In linear algebra, one thing we can do is make a transformation on vectors that takes each vector to its negative. In a sense, it inverts all of space, so let's call this operation inversion. By definition, it takes each vector to its negative. Now, one interesting thing is that in 3D there are some vectors that once you have done inversion, don't change sign. How can this be? Well, one explicit example arises from the use of the evil cross product. Now, if you haven't heard about the cross product before, all you need to know is that it takes in two vectors and produces a third vector. If you do an inversion, the two input vectors change sign, and then the minus signs cancel, so the result of the cross product does not change under an inversion. Because these vectors act differently than normal vectors under inversion, people call them pseudovectors. Some examples of pseudovectors in physics are angular momentum and the magnetic field. Whenever you are doing certain transformations like inversions and reflections, you need to keep track of whether your vectors are true vectors or pseudovectors so that you get the correct results. There's something similar with scalars too. Scalars, not having any vector components, should not change sign under an inversion. However, some scalars change sign anyway. The scalars that do change sign under an inversion are called pseudoscalars. Now let's look at how the objects in geometric algebra act under inversion. Like usual, ignoring pseudoscalars and pseudovectors, scalars are unchanged and vectors get negated. For a bivector, notice that when you invert an entire bivector, the orientation doesn't change. Another way of thinking about it is that bivectors are made from two vectors, and when each vector individually gets negated, the two minus signs cancel out when making the inverted bivector. So, bivectors don't change sign under inversion. And while I haven't described how to visualize trivectors yet, if we think about them as being made up of three vectors, we see that inversion creates three minus signs, which simplifies down to one minus sign. This argument is a bit hand-wavy, but that's because we haven't yet covered the tools needed to make this argument rigorous. However, it is true that trivectors change sign under inversion. So scalars don't get negated, vectors do, bivectors don't, and trivectors do. Now I want to compare this to the behavior of scalars, vectors, pseudovectors, and pseudoscalars for a moment. Scalars don't change sign under inversion, vectors do, pseudovectors don't, and pseudoscalars do. Notice that the behavior of the objects lines up. And this matching goes even further. Since we are in 3D, both pseudovectors and bivectors have three components, and both pseudoscalars and trivectors have one component. Could it be that what everybody has been calling pseudovectors and pseudoscalars are really just 3D bivectors and trivectors? I would say that the answer is yes. Since vectors and pseudovectors behave differently, they should not be the same object. Furthermore, in each case that we have a pseudovector, it just makes more geometric sense for the object to be a bivector than a vector. For example, angular momentum is traditionally said to be perpendicular to the plane of rotation. However, if angular momentum was a bivector, it could instead be oriented in the direction of rotation. Because of all of these reasons, In geometric algebra, we never use pseudovectors or pseudoscalars in the traditional sense, and instead only use things like bivectors and trivectors. Since they fulfill the same role as traditional pseudovectors and pseudoscalars, those of us doing geometric algebra started calling the 3D bivectors and trivectors pseudovectors and pseudoscalars. While traditional pseudovectors and pseudoscalars exist in only 3 dimensions, in geometric algebra, we can generalize these ideas to other dimensions. I'll talk more about that generalization in a future video. The other main thing I want to bring up in this video is tensors, or more specifically, antisymmetric tensors. Now, I don't want to describe tensors in this video since it's a massive topic, so I'll just focus on the actual results. In places where we use k-vectors in geometric algebra, others sometimes use antisymmetric tensors. For a particular example, given a general 3D bivector, this antisymmetric tensor in some senses represents the same object. For a more complicated example, in 4-dimensional spacetime, we can represent the electromagnetic field using a bivector or this antisymmetric tensor. While describing these objects with antisymmetric tensors does work, it feels like overkill. Tensors are very powerful objects, and as a result, can represent many things. However, if you were given some random antisymmetric tensor, would you think of it as an oriented plane segment? No! Math in general is a tug-of-war between abstraction and clarity. In every context, we need to figure out what gives us a good balance between these two things. I would argue that using tensors to describe what we can describe with k-vectors is going too far away from clarity. In general, we shouldn't use tools that are so powerful that we lose the intuition behind what we are talking about. Now, don't get me wrong, tensors are a useful tool, but not for when we are talking about concrete geometric objects like lines and planes.